Hi! Welcome back to our class in Analytical Chemistry. Today, I will be discussing about the reaction rates and chemical equilibrium. It is said that the rate of reaction is a quantity that tells how the concentration of a given reactant or product changes with time. It is defined by the equation rate of reaction equals a change in concentration over time. So this change in concentration would refer to the concentration of the given reactant or the concentration of the given product. Why is it that it's important to study about this rate of reaction? It is because there are practical applications in the study of a rate of reactions. This includes, number one, especially in industry, to know how feasible the reaction is. It is important to find conditions that give a desired product at a reasonable speed in order to be economically feasible. Second is, reaction rates are important in areas as the growth of plants and in refrigeration of food to prevent it from spoiling. Because we know that when the food is not refrigerated, then the rate of reaction in terms of its decomposition reaction would be fast. Because we know that at a lower temperature, the reaction is slow, and in higher temperature, reaction is fast. So if you don't refrigerate the food, reaction will be fast. Because we are talking about reaction rates, what are some examples of these reaction rates? There are reactions in which they are so fast or drastic, and there are also reactions which are very slow. What are some examples of these very fast reactions? Number one, we have the reaction of a sodium metal with water. You know, the sodium metal, when placed into the water, will really explode. We have tried this in the chemistry laboratory. And another fast or drastic reaction is the explosion of a dynamite powder. So it is very, very hazardous to inflame or enkindle a dynamite, because you might not know that while you're still holding the dynamite, it might explode. Why is it that dynamites are also produced? In mining operation, the dynamite is used to blast out the mountains or those areas in which they are going to mine. So that is the use of the dynamite. It is not to be used for fishing, by the way. On the other hand, there are also very slow reactions, such as a change in rock structure. Another is the formation of coal and petroleum. These are very, very slow reactions. There might be a reaction that is formed, but it takes million years to form coal. It takes million years to form the petroleum. Now, talking about reaction rates, there are some related terms which is necessary to be learned. One is the chemical kinetics. When we say chemical kinetics, it is a study of reaction mechanisms and reaction rates. It is concerned with reaction rates, wherein it deals with the rate of change from an initial to the final states under non-equilibrium conditions. Reaction rates, by the way, determines how fast a reaction will occur or will proceed. And for a reaction to occur, the reacting molecules of a substance must collide to each other with sufficient energy. Now, this sufficient energy is referred to as the activation energy to overcome any force of repulsion between the electrons. And what is this reaction mechanism? This reaction mechanism refers to a stepwise change involved before a reactant or reactants are converted into products. What is another term related to the study of reaction rate is the activation energy. When we talk of activation energy, it is the amount of energy required for collision to produce a successful reaction. There are evidences of a chemical reaction. Number one, we have evolution of gas. I think you have observed in our laboratory experiments that when there is a reaction that occurs, there are gases that are evolved or bubbles are formed. What are some examples? When the aluminum shavings was added with hydrochloric acid, take note that there was a gas evolved. Much bubbles were formed. Another one is the appearance and disappearance of color. Most of our chemical reactions in the laboratory produced different kinds of color. For example, in the appearance of a color is when you added or reacted the ferric chloride with sodium hydroxide. Take note that you are able to form the ferric hydroxide as an orange or rusty orange color. So there was an appearance of color. An example of a disappearance of color, what was it? When the chromic oxide was added with the 6-normal sodium hydroxide, what have you observed? The green color of the precipitate disappeared. Then another evidence is the formation of a solid. So this is what is meant by the formation of a precipitate. A solid is a precipitate. So there are many examples or many experiments that we have had in the chemistry laboratory wherein a solid was formed. For example, when we reacted the silver nitrate with sodium chloride, it formed silver chloride, which is a white precipitate. Then we have the disappearance of solid particles, meaning the solid particles were dissolved, and an energy change. So when we say energy change, there are reactions in which when you added the reagents, it formed a hot reaction, or you can feel that the reaction is hot, and there are those in which you can feel that the reaction is cold. What is a good example wherein the reaction is hot? When you added aluminum shavings with an acid, for sure the reaction is hot. So it is exothermic, isn't it, when heat is being evolved. But when you added ammonium chloride with water, when you feel the reaction, it felt cold. So it's endothermic. Now, let's go to what are the factors affecting the rate of reaction. We have 4 factors that affect the rate of reaction. Number 1, we have the nature of the reactant, we have temperature, we have presence and absence of catalyst. Then number 4, we have the concentration of reactants. Let's discuss them one by one. Number 1 is the nature of the reactants. This refers to the type of chemical bonds present in the reacting substances. The more the chemical bonds of the reacting substances are alike, the faster is the rate of reaction. This means that ionic substances will react with each other. Covalent substances will react with each other. Good example for this, we have number 1, the sodium chloride will dissolve fast in water. Why? Because the sodium chloride is a polar substance, while water is also a polar substance. And there are other examples that I gave there. Another is the sodium metal plus the water. It will give us a very fast reaction. But on the contrary, the gold, when reacted with water, this will not react fast. This will not react fast. There is no reaction. Does not even tarnish in many years of exposure. Another example is that when a covalent substance reacts with another covalent, like most of these covalent substances are the organic substances. For example, the oil dissolves fast in a nonpolar solvent. For example, the vegetable oil or any kind of oil will dissolve readily in carbon tetrachloride, wherein this solvent, carbon tetrachloride, is a nonpolar solvent. Another factor that affects the rate of reaction is the temperature. Now, as the temperature increases, the rate of reaction is fast. Why is this so? This is because as the temperature increases, the kinetic energy of the reacting substances also increases. That means if there is a high kinetic energy, more collision between the reacting substances will occur. And if there is more collision, then the reaction is made fast. Another factor affecting the rate of reaction is the presence or the absence of the catalyst. When we say a catalyst, it is a substance that speeds up the rate of reaction without itself undergoing a chemical change. Now, the catalyst usually hastens the speed of a chemical reaction. And there are those negative catalysts, by the way, and they are called the inhibitors. What are some examples of these catalysts? In the chemistry laboratory, we have a catalyst that is commonly used in decomposing the potassium chlorate into potassium chloride and oxygen, which is manganese dioxide. So this manganese dioxide is being mixed with that of the potassium chlorate, and then when this mixture is heated, the decomposition reaction is made fast. So the formation of the oxygen is made fast. Now, what are some examples of these negative catalysts or the inhibitors? One good example is the paint. If you notice, your roofs, which are made of galvanized iron, usually rusts or get rusted after 3 years or 4 years of exposing to the heat of the sun. There is the wear and tear that could happen, leading to the rust formation. Because we know that the galvanized iron, once the zinc is corroded, then the iron will be exposed out. When this iron is exposed to the atmosphere, then this will be reacted with the oxygen to form the rust or forming the rust. Now, how will this rust formation be hindered? So this formation of the rust in our galvanized iron is hindered by applying paints. So a paint is a good inhibitor. It's a negative catalyst. Another factor affecting the rate of reaction is the concentration. That means the higher the concentration of the reactants, the faster is the rate of reaction. So those are the factors that affect the rates of reaction. Now, it is said that all reactions are classified as either homogeneous reaction or heterogeneous reaction. When we say homogeneous reaction, this is a reaction wherein there is only one phase exhibited between the reactants and the products. That means if the reactants are all gases and the product is a gas, so this is an example of a homogeneous reaction. Or if the reactants are all liquid and the product formed is also liquid, so this is an example of a homogeneous reaction. A good example here is the reaction between nitrogen and hydrogen forming ammonia gas. We know that nitrogen is a gas reacting with hydrogen, which is also a gas, and the product is ammonia, which is a gas. This is a good example of a homogeneous reaction. While a heterogeneous reaction is that if more than one phase exists in a reaction mixture. A good example for this is the burning of the wood. Why? Because in the reactant, the wood is a solid, and when it forms its product after burning, you have there the carbon dioxide as a gas released, and then there is the charcoal as a carbon that is formed. Another one is that of the discharge of the automobile. Okay, the formation of the discharge of the automobile, it starts from being a liquid, the gasoline, and while this is combusted by the engine, then it has the exhaust, the carbon dioxide as a gas. So two or more phases exist in the reaction. Now let's go to the chemical equilibrium. A chemical equilibrium is a state where the concentration of all reactants and products remain constant with time. So there is the state where the concentration of all the reactants and products remain constant with time. It is a state when the rate of the forward reaction is equal to the rate of the backward reaction, meaning the rate in forming the products is equal to the rate in forming back the reactants. So the forward reaction is equal to the backward reaction. Now there are types of chemical equilibrium. One, we have the irreversible reaction, and the other one is the reversible reaction. When we talk of irreversible reaction, this is a type of reaction that goes to completion, meaning you cannot get back what are the reactants from the formed products. Example of this, we have formation of insoluble gas. Another is the formation of an ionized substance. Another is the formation of an insoluble solid. What could be a good example that we have done in the laboratory? That is, when we form the precipitation reaction between barium chloride and sulfuric acid. So what was the product formed? It is barium sulfate. Another is when we reacted the ferric chloride with sodium hydroxide. So the precipitate form there is ferric hydroxide, in which you cannot get back from the ferric hydroxide, the ferric chloride, and the sodium hydroxide. So those are some examples of irreversible reaction, meaning these reactions will really go to completion, can no longer be taken back. While those reversible reactions, this is what we're going to study because this is a chemical equilibrium. Those are reactions wherein the products of a chemical change can react to form back the reactants. So this is given the general pattern, which is if the reactants are A and B, forming the products C and D, in the formation of the products C and D, these products C and D will form back the reactants A and B. That's why this is represented by a double arrow. One arrow pointing towards the left and another arrow pointing towards the right. Meaning That arrow pointing towards the left is the forward reaction, while that arrow pointing to the right is the backward reaction. So this pattern, which is A plus B double arrow, C plus D, is a system in the state of equilibrium. So what are some examples, real examples of this? For example, if you're going to decompose the water, so how do you decompose water? It is through application of electrical current. So there is electrolysis formed. Now, when the water is decomposed, you have the products hydrogen plus oxygen. Now, this hydrogen and oxygen, when they react, can form back the water. So there is a state of equilibrium between the decomposition of water and the formation of water molecule back. Another one is the reaction between nitrogen and hydrogen. In the reaction between nitrogen and hydrogen, there is a formation of the ammonia gas, plus of course the liberation of heat. And this reaction between nitrogen and hydrogen, forming the ammonia, can form back the formation of nitrogen and hydrogen from the product, which is ammonia. Another is the formation of hydrogen iodide gas. When hydrogen reacts with iodine gas, then it forms the hydrogen iodide. And this hydrogen iodide gas can form back the hydrogen and the iodine gases. Talking about the system in equilibrium, it has three characteristics. One, there are two opposing reactions. What are these reactions? We have the forward and the reverse reaction. Number two, both reactions are in full operations at equal speed, and any change in condition, such as the concentration, pressure, and temperature, produces a corresponding change in the system. So those are the three characteristics of a system in equilibrium. Considering the general equation, which is A plus B double arrow C plus D, when A and B are mixed, they will react at a rate that depends on their concentrations at this instant. As they react, their concentrations will decrease. Why? Because they start already to form the product, so their concentrations will decrease. Number two, collisions between them will become fewer because the reactants now starts to be used up. And thirdly, the speed of the forward reaction will decrease. So from left to right reaction, so the speed now starts to decrease. At first, during mixing, there will be no production of the products C and D molecules yet. But as the forward reaction begins, the concentration of the product C and D increases. And the rate of the backward reaction also increase. Why? Because there is already the formation of the product C and D, and these C and D products are responsible in forming back the reactants A plus B, thus establishing a state of equilibrium. This is explained by what we call the Le Chatelier's principle. In Le Chatelier's principle states that if a stress is applied to a reaction at equilibrium, the equilibrium will be displaced in such a direction as to relieve that stress. So what does that mean? If you have a reaction which is in equilibrium, meaning the rate of forward reaction is equal to the rate of the backward reaction. And at that very state, the state of the reaction is balanced and in equilibrium. However, if a stress is applied into the state of a reaction in equilibrium, what will happen to the reaction which is in the state of equilibrium? This equilibrium will be displaced in such a direction so as to relieve that stress. So it has to make a shifting, or it has to make movements in order to relieve that applied stress. What are some of these factors that affect the state in equilibrium of the reactions? One is the effect of the concentration. So increasing the concentration of the reactant increases the number of collisions between reactant molecules so that the rate of the forward reaction is greater than the rate of the reverse reaction. Now, where will the shifting of the reaction go if you will increase the amount of the reactants? Say, for example, increasing the concentration of substance A or reactant A, and or increasing the concentration of the reactant B. So if you're going to increase their concentrations, so that in order for this reaction to remain in equilibrium, so the reaction should shift to the right to establish an equilibrium reaction. However, if you're going to remove the products C and D, then there is again the decrease in the concentration of the product. Now, where will the direction of the shift go? So the direction will be towards the right again, so that the reaction will remain to be in equilibrium. Another factor that could affect a state in equilibrium of a reaction is the effect of catalyst. The addition of a catalyst will speed up the forward reaction, but will also speed up the reverse reaction equally, because we said that when there is the presence of the catalyst, then the rate of the reaction will be hastened or made fast. Now, since this is in a state of equilibrium, so the rate of forward reaction is equal to the rate of backward reaction or the reverse reaction. So upon the addition of a catalyst to the reactants will make the reaction fast towards the product formation. And when there is already the products formed, then the presence of the catalyst also hasten to form back the reverse reaction. So what would be the effect of the presence of the catalyst? So naturally, the catalyst will have no effect on the equilibrium reaction. Another is the effect of temperature. When we say the effect of temperature, as the temperature increases, then the reaction will be made fast. So in the case wherein the reaction given there is the hydrogen chloride reacted with oxygen to form the water and the chlorine gas, presuming that these are all gases or a homogeneous reaction, in the sense that the hydrogen chloride is a gas, the oxygen is a gas, forming also the products water in a gaseous state and the chlorine in the gaseous state. Thus, this is considered as a homogeneous reaction. And there is the release of heat in the product formation. Heat is liberated when the reaction proceeds to the right and is absorbed when it proceeds to the left. What do you mean by that? In the forward reaction, heat is liberated because we applied here an increase in temperature. But in the reverse reaction, heat is absorbed. Now, if the temperature of this reaction is raised or increased, then the equilibrium reaction will go to the direction to relieve this stress. That is, as the temperature is raised, the equilibrium will shift to the left. Why? Because look at the reaction, there is already the heat released at the right. So, increasing the temperature will make the reaction shift to the left, favoring the reaction that tends to absorb this heat so that the reaction will remain to be in a state of equilibrium. Conversely, as the temperature is lowered, so we will decrease or remove out the temperature, the reaction speeds more to the right for the production of more heat to relieve that new stress. Let's go to number 4, the effect of pressure in an equilibrium reaction. Now, increasing the pressure increases the concentration of all the gases involved in an equilibrium reaction, and decreasing the pressure has the opposite effect. The side that has most number of moles of gases is the side that is more sensitive to pressure change. So if we assume in that reaction that I gave a while ago, which is the reaction between hydrogen chloride gas and the oxygen gas forming the water gas and the chlorine gas. So if you're going to get the number of moles of the reactants, we have a total of 5 moles. And if you're going to get the number of moles of the products, it is only 4 moles. So it is said when there is the most number of moles present in either side, whether it is in the reactant side or in the product side, this side wherein there is the most number of moles is sensitive to pressure. And because it is sensitive to pressure, so the reaction will go to the other side, or there is an opposite effect. So in this case, because in the left side there is more number of moles of gaseous reactants, therefore this is more sensitive to the addition of pressure. So if a pressure is to be added to this reaction in equilibrium, then the reaction would shift to the right. However, if the pressure is decreased, then the reaction would shift to the left. So those are the factors that could give a stress to a reaction in equilibrium. Then let's go to the equilibrium constant. Now this equilibrium constant is represented by the symbol K sub P. It is said that the partial pressure of a gas is a measure of its concentration. Equilibrium constants for reactions involving gases therefore may be written in terms of the partial pressure of the reacting gases. An equilibrium constant of this type is given the designation K sub P. A good example for an equilibrium reaction is that of the calcium carbonate forming its products, calcium oxide and carbon dioxide gas. So in the beginning, calcium carbonate is a solid forming calcium oxide, which is a solid, and carbon dioxide is a gas. So what kind of reaction is this? This is a heterogeneous reaction. Now, since the equilibrium constant is concerned more of the gases or the gaseous part in a chemical reaction, so for that reaction between carbon, so for that reaction of the calcium carbonate forming the calcium oxide and the carbon dioxide, the equilibrium constant therefore for this reaction is K sub P is equal to the partial pressure of the carbon dioxide. Why only carbon dioxide? It is because it's the only gas in the chemical reaction. Another one. For the chemical equilibrium reaction between nitrogen and hydrogen forming ammonia, if you're going to look at this reaction, all the reactants, nitrogen and hydrogen, are gases, and it forms a gaseous product. So what will be the formula for this K sub P? So in this case, we have K sub P equals the partial pressure of the ammonia gas divided by the products between the partial pressure of the reactants, which are the nitrogen and the hydrogen. But when you write the K sub P, or the equilibrium constant for this reaction, you have to balance the chemical reaction first. Now, in balancing the chemical reaction, you need to put a numerical coefficient in hydrogen, which is 3, and you have to put a numerical coefficient in ammonia as a product, which is 2. Now, since the equilibrium constant is the ratio between that of the product, considering the coefficient, and that of the reactant, considering also the coefficient, so if you're going to look at the formula there, it is K sub P equals the partial pressure of ammonia squared over the partial pressure of nitrogen times the partial pressure of hydrogen cubed, or raised to the exponent 3. Why so? Because in the balance equation, you have the nitrogen has a 2 coefficient, and in the reactants, you have the hydrogen has a coefficient of 3. So these coefficients become the exponents when you are going to write the equilibrium constant for the reaction. So to give a general formula for the equilibrium constant, it is to consider also the coefficients of the balanced chemical reaction. For example, if there is a reaction between W and X forming the products Y and Z, such that W has a coefficient W and X has a coefficient of X, and forming the products Y with a coefficient of Y, and the second product, which is Z, with a coefficient of Z. So how does your reaction read now? So you have now the reaction, which is W plus X forming the products Y plus Z. The small letters representing the coefficients, while the big or the capital letters representing the reactants and the products. So a while ago I said that if you have gaseous reactants and gaseous products, so the general formula, or the formula for the equilibrium constant, will be the K sub P equals the ratio between the partial pressure of the products over the partial pressure of the reactants. Now, since in this case, if we consider that the W, X, Y, and Z are all gases, so you have to get the product of the products and the product of the reactants, considering their coefficients. That's why in that general formula, you have K sub P equals the partial pressure of Y raised to the exponent Y times the partial pressure of Z raised to the exponent Z, divided by the partial pressure of W raised to the exponent W times the partial pressure of x raised to the exponent x. So notice, so if you're going to look at your notes there, the final equation for the equilibrium constant governing that equation, which is between the w and x forming y and z, is K sub p equals the partial pressure of y raised to the exponent y times the partial pressure of z raised to the exponent z, all over or divided by the partial pressure of w raised to the exponent w times the partial pressure of x raised to the exponent x. Then, if we assume that each gas behaves or follows the ideal gas law, so to recall the ideal gas law, which is PV equals nRT. I think you have remembered this when we had our boiling point elevation and freezing point depression. We have PV equals nRT, or you remember this when we had the concentrations of normality, where the P here is the pressure of the gas, V here is the volume of the gas, N is the number of moles of the gas, where R is a constant with a value of 0.08206, and the unit is liter atmospheres per mole per degree Kelvin. So you are going to use that in substituting for the value of R, and the temperature is in Kelvin. Then the partial pressure of any gas, P, is P equals N over V times RT. So take note that N over V, or number of moles per liter solution, can be a molarity. So this can be substituted by a molarity in some cases of the problems. So what will happen now? The concentration of a gas in moles per liter is equal to N over V. As I have said a while ago, N over V again is moles per liter. So this can be a concentration of a gas. Therefore, for a gas W, the partial pressure of this gas can be written as W enclosed in a bracket, wherein this bracket implies a concentration, times RT. So, take note, the bracket enclosing W is an expression that is a concentration of the reactant W. Then let's go to the next reactant. Therefore, you have partial pressure of W raised to the exponent W equals the concentration of W raised to the exponent W RT. Now, if we consider the other reactants like Y, so the partial pressure of Y is equal to the concentration of the reactant Y, so placed inside the bracket, raised to the exponent Y, RT. So the formula will become, finally, for the equilibrium constant Kp for these gases will become K sub P equals the product of the products over the product of the reactants. So you have the concentration of the product Y raised to the exponent Y, because Y is a product, times RT raised to the exponent Y, times the concentration of the product Z raised to the exponent Z times RT raised to the exponent Z, all over or divided by the concentration of W raised to the exponent W times RT raised to the exponent W times the concentration of X raised to the exponent X times RT raised to the exponent X. Take note, RT is common, so you can factor it out. So you can express RT as RT of Y, RT of Z, and RT of W, and RT of X. In mathematics or in algebra, isn't it, if you have A to the M divided by A to the N, this can be expressed as A M minus N. Okay, can you recall that in your algebra? So we can now express RT as RT raised to the exponent Y plus Z minus W minus X. That is based on Endix laws, which is A to the M divided by A to the N equals A to the M minus N, following that law. The fractional term in the last equation is equal to K sub C. Where is that K sub C? That is referring to the concentration of the products Y and Z divided by the concentration of the reactants W and X. So, because these are expressions of concentrations, we can represent it by K sub C. So, what will happen to the final formula of the equilibrium constant K sub P? This will become K sub P equals K sub C times RT raised to the exponent Y plus Z minus W minus X. Now, we know that the Y and Z are the number of moles of gases on the right, and W and X are the number of moles of gases at the left. So, we can let delta N, or a change in number of moles, delta N, equals the change in the number of moles of gases in the equation. So, delta N will represent the change in number of moles of the products, that is Y plus Z minus W plus X. So, we can express now the formula for the equilibrium constant as K sub P equals K sub C times RT raised to the exponent delta N, where K sub P is the partial pressure and it is expressed in atmospheres. The K sub C are the concentrations of the reactants and the products, which are expressed in moles per liter or molarity. Then R is the constant, which has a value of 0.08026 liters atmospheres per mole per degree Kelvin. And the T is the temperature, or the absolute temperature in Kelvin. So I have there an example in the determination of the K sub P for the following reactions. For example, a reaction between the phosphorus pentachloride forming the phosphorus trichloride and the chlorine gas. If you are going to balance the reaction, it is, you have there 1 mole of phosphorus pentachloride equals 1 mole of phosphorus trichloride plus 1 mole of chlorine gas. So what would be your equation there for the equilibrium constant? So it will be equilibrium constant equals K sub P equals K sub C times RT raised to 1 or positive 1. Why 1? Because in the products you have 2 moles of gases, that of phosphorus trichloride, and chlorine gas. So you have 2 moles at the right. So the products, in the product you have 2 moles of gases, and in the reactant you have only 1. So 2 minus 1. So your delta N there is plus 1. Let's go to the second reaction. A reaction between carbon monoxide and chlorine gas, forming the carbon oxychloride. So if you're going to balance the reaction, you have 1 mole of carbon monoxide plus 1 mole of chlorine gas. Therefore, you have 2 moles in the reactant, 2 moles of gases in the reactant, and 1 mole of gas in the product. So what will be your delta N there? So delta N equals 1 minus 2 is negative 1. So you can write it as K sub P equals Kc divided by RT. Because in algebra, if the exponent is negative, you can bring that negative term down as a denominator to make it a positive. Then for the third reaction is hydrogen gas reacts with iodine gas, forming hydrogen iodide. Now, if you're going to balance the equation, you have 2 moles of the reactant gases is equal to 2 hydrogen iodide gas. So you have also 2 moles of gases in the product. So what will be your delta N? So delta N there is 2 minus 2 is 0. So what will happen to your formula? It is K sub P equals K sub C times Rn raised to the exponent 0. But we know in algebra that when anything or any term with raised to the exponent 0, the value of that term is 1. So Kp is equal to Kc. So that's all about the equilibrium constant. Let's go to ionic equilibrium. The principle of chemical equilibrium can be applied to equilibrium systems that involve molecules and ions in water solution. In pure water, hydronium ion and hydroxyl ion exist in equilibrium with water molecules from which they are derived. Weak electrolytes are partially ionized in water solution and exist in equilibrium with their ions. And understanding of these systems is important to the study of analytical chemistry. Let's start with the first, ionization of water. Now, pure water is itself a very weak electrolyte and ionizes according to the equation. Water plus another water molecule will form a hydronium ion plus the hydroxyl ion. In simplified form, this equation is water is in equilibrium with hydrogen ion and hydroxyl ion. The expression for the ionization constant derived from the simplified equation is K is equal to, so product of the products, so you have the concentration of the hydrogen ion times the concentration of the hydroxyl ion all over the concentration of water. Now, in dilute solutions, the concentration of water is a constant, and we may combine water with the constant K. So if you're going to look at there, the concentration of water, K times the concentration of water, is equal to the concentration of the hydrogen ion times the concentration of the hydroxyl ion. Now this constant of K times concentration of water is called the ion product of water, or the water dissociation constant, and is given the symbol Kw. So that is, repeat, the water dissociation constant, and is given the symbol Kw. And at 25 degrees centigrade, Kw equals 1 times 10 to the negative 14 equals the concentration of the hydrogen ion times the concentration of the hydroxyl ion. And in pure water, if we let X to be the concentration of the hydrogen ion and let X also is the concentration of the hydroxyl ion, so if you're going to write their equation, it will become the concentration of the hydrogen ion times the concentration of the hydroxyl ion equals 1 times 10 to the negative 14, equating this to the concentration of the hydrogen ion and the concentration of the hydroxyl ion. If we represent that a while ago as X, so you have X times X equals 1 times 10 to the negative 14. So you have X times X equals X squared equals 1 times 10 to the negative 14. Therefore, X equals the square root of 1 times 10 to the negative 14 is 1 times 10 to the negative 7 molars. So the concentration of both of the ions in water is equal to 1 times 10 to the negative 7 molars in pure water or in any neutral solution. So that's why when we go to pH, the exponent 7 there implies a neutrality. And I gave you some examples there, and I think they are easy to understand, so kindly go over those examples. And for the last topic of this chapter, we'll go to weak electrolytes. Now, what are these electrolytes? Electrolytes are those substances which conducts electricity when in solution. Now, talking about electrolytes, there are the weak electrolytes and there are also strong electrolytes. Most of the inorganic substances, like the metallic, especially the metallic elements, they form strong electrolytes. Why? Because they easily dissociate into ions. However, most of the organic substances forms a weak electrolyte. A good example for the weak electrolyte is the acetic acid. Why? Because acetic acid does not readily form its ions. It requires 2 to 3 steps to dissociate acetic acid into its ionic form. So in that equation that I gave there, the CH3COOH plus water will form the hydronium ion and the acetate ion. So actually, the CH3COO there is the acetic acid. When added with water, or reacted with water, will form the hydronium ion and the acetate ion. So the equilibrium constant for this reaction of the weak electrolyte, which is the acetic acid, can be represented as K sub A equals the product of the products divided by the product of the reactants. So it is the concentration of the hydronium ion times the concentration of the acetate ion divided by or all over the concentration of the reactants, which are the acetic acid times the concentration of water. In dilute solutions, the concentration of water may be considered to be a constant. That is, the number of moles of water used in forming hydronium ion, which is about 0.001 mole in 1 liter of a 0.1 molar solution of acetic acid, is very small in comparison to the large number of moles of water present, which is about 55.5 moles in 1 liter of a solution. So if we combine the concentration of water with the K sub A, or the ionization constant, we get concentration of the hydronium ion times the concentration of the acetate ion divided by the concentration of the acetic acid. Why? Because as I have said a while ago, the number of moles of water used in forming the hydronium ion is very, very small. That's why the water concentration there is no longer considered. So, if we shall follow the practice of representing the concentration of hydronium ion to be hydrogen ion, then the simplified expression for the equilibrium constant K sub A, or sometimes called as the dissociation constant, we can represent the equation as dissociation constant K sub A equals the concentration of hydrogen ion times the concentration of the acetate ion divided by the concentration of the acetic acid. And I gave there an example of solving the dissociation constant for weak electrolytes. So kindly go over it and please study these notes, because on Wednesday I will give a quiz. And kindly take note also of your assignment which I gave for the laboratory. Kindly keep in touch with your mayors, by the way, because you are assigned to a certain group. And I want you also to submit your requirements starting Wednesday to the chemistry lab. I have sent a photo on how to compile the requirements. Please follow them accordingly, so that when I look for your requirements, your compiled experiment reports, as well as the quizzes and the exercises in the lecture, I will not get lost, and your work will not also be lost. So those are all for today. Kindly be prepared for a quiz on Wednesday. And this is your teacher, Professor Nisitas Ruiz of Holy Name University.